Good afternoon, everybody. Welcome to another overcast but fun-filled afternoon of Chem 170 with your host, me, Dr. White. All right, important thing. Let me remind you. Let me open it up first. Every thumbs up, people. Did you see Chem 170 test number 1 information? Thank you. All right, week from today, I will be giving test number 1. Test number 1 has 10 pages, 14 problems. Some of the problems are multiple part, like I've done my questions, my problem set A, B, C, and D, and so on. I will never in Chem 170 and never have, never will have multiple choice. I don't like those. It will cover the alkanes, that includes cycloalkanes, alkenes, double bonds, alkynes, triple bonds, and aromatic compounds, which I just about finished up on Monday. And here's the point breakdown for test number 1. There'll be 13 points on general knowledge. What's general knowledge? Well, how many bonds to carbon? 4. Hope we all got that down by now. And it will have 45 points in nomenclature. 2 main questions I can ask. Here's the molecule, give the Iupac name, or here's the name of a molecule, draw it. For this test, the only common name I've asked you to learn is acetylene. And finally, 47 points on reactions. And that's all but one question will be, give the reaction product or products for the following. The one that won't be like that, I'll have only one synthesis problem. That's give the starting materials for this reaction. And that one type of question can be for any of the general reactions I've covered for material on test number 1. And if you notice, it adds up to 105 because there's 5 bonus points. You pick the bonus points. All right. First of all, when it comes to my test, every question on the test, except where you got to write your name, is I have covered at least twice, more than twice, usually a lot more, in a lecture. Nothing in the lab will ever be on a test. And you'll have enough time to do it. The way I will be giving the test number 1, also 2, 3, 4, and the final is on the day before the test, Tuesday, I will upload and create an assignment in D2L, which will have test number, in this case 1, PDF file. It will be password protected. You can't open it up. And right after class on Wednesday, when I finish, I will send out an email to all of you with the password. You have until 10 a.m. Thursday to take the test, scan it or take pictures of it, and make a PDF file and upload that PDF file to D2L. Take about, if we were face-to-face, I give students, we have 50 minutes, but I give them 55 minutes because we got to go do the lab afterward. Just like we'll do a lab today and also next Wednesday. However, since there's no class or anything where we got to get to the lab, if you need an hour, go right ahead. However, I can tell you this from teaching Chem 170 a number of times, and that is, if you've done the practice problems, I hope you have, and you've studied a little, my tests usually take 35, 40 minutes to finish, but take an hour or so. You should not go on the internet. You should not look at your notes, and you should not get help from anybody else. Trust me, I put secret things, I'm not going to tell you, in my test that I can tell when somebody's cheating. And unfortunately, I have caught a very small amount, but I have caught students cheating since we went to Zoom, and what's in my syllabus I do. So please don't cheat. All right, any questions about test number 1? Ooh, stop finger, stop. Oh no, it's totally obnoxious Humor Wednesday. You got to suffer through it just like I do. Stop. But anyways, any other question? Well, I've got a question for you. Anybody drive by a gas station and think about, wow, in the gasoline they sell, they're alkanes? Did you do that? Did you happen to cook with natural gas and say, oh, the flame that's burning, that's combustion, and the natural gas is methane? That's an alkane. I don't know if anybody did any barbecuing last week or two. I had a friend who used to live in the area. He moved out of the area. That's why we lost contact with each other. But he would barbecue as long as he could get this barbecue, whatever the weather, he'd barbecue. Well, it was 5 below. No, I'm not going to do barbecue. Trust me, I won't. But he would. All right. Did anybody happen to look at Vaseline or baby oil, or maybe a good candle, and think those all contain alkanes? Remember, when you leave my class, organic chemistry is all around you. I stole that from SpongeBob. But anyways, and it won't hurt for you to think, trust me, I'm a doctor. It won't hurt for that word. It won't hurt for you to think about organic chemistry when you're not with me. It's everywhere. And think about gasoline. Next time you go by a gas station, think about they're selling alkanes. All right, today I promised I'd go through the alkenes and alkynes problem set. Now, some of you can't always make it to class, and you're probably watching this on the video, me drinking tea. But anyways, one of your colleagues who didn't feel comfortable asking questions in class sent me an email, asked if I could go over some questions, and that's a good idea. So if you ever have stuff when I'm going over a problem set, and I'll do it, and if you can't make it here, it will be in the video. All right, let's go to the problem set. And remember, there's no such thing as a dumb question. And question number 1, and hopefully you all can see the alkenes problem set on your thumbs up, people. Can you see it? Thank you. All right, problem 1, and this is a nomenclature question. Thank you, Vivian, and also to you, Danielle. Give the Iupac, and Iupac means official name, even though Dr. White, me, likes to say International Union of Pure Applied Chemistry, because it sounds cool. Give the Iupac name for the following. When you're looking at a molecule, look for what's different. What's not a carbon-carbon single bond or a carbon or hydrogen should get your attention like that. And if we look at the first one, we have a double bond. And how do we do double bonds? Find the longest chain that has both carbons double bond. That's 4. Name it as an alkane. Hopefully you learned that chart. Butane. It's a double bond. Drop the A on the ending, put E on E. Butene. Now here we have what carbon of the 2 carbons is closest to the end. That should get the lowest number. Notice when we start here, that's carbon 1, and that lead carbon is 1. If I started on the other side, the lead carbon double bond would be 3. Remember, the math in this class is real difficult. You have to know what numbers between 1 and 10 are larger and smaller than the others. Now, if we all pick 1 is smaller than 3, so that's 1 butene. When you have 2 of the same atom or group on one of the carbons of the double bond, 2 hydrogens here, you can't have sister trans isomerism. So we don't. Now, let's go to D, and then I'll come back to B. If you want me to do any of them I skip, always feel free to ask. Now, the question is, what's the Iupac name for D? Well, you have to find the longest chain with both carbons of double bond. So here's 1, here's 2, here's 3, here's 4. Now, at first glance, somebody said, oh, there are 2 methyl groups on there, and I'm done. No, this carbon right here is bonded to the methyl groups. So the one on top or the one on bottom is continue of the chain. So it's 1, 2, 3, 4, 5. And that would be pentane. It's a double bond. So you drop the A on the ending, put E on E, pentene. which carbon of the double bond is close to the end of the chain? Well, we don't know. This is 1. It would be 2 if I start from the right. If I start from the left, 1, 2, 3. Which is smaller, 2 or 3? And the answer is 2. So it's 2-pentene, which means there's still one CH3 group. Oh, it's your old friend, the methyl group, CH3, and it's on carbon 2. And that's how you do it. Now, why don't you have cis or trans? Because if you notice on one of the carbons, there are 2 CH3 groups. When there are 2 atoms, the same atom, or 2 of the same group on the same one of the carbons of the double bond, you don't have cis or trans. Now let's look up at C, and see here we have a double bond, longest chain, 1, 2, 3, 4, 5. And that would be pentane. Again, drop the ANE, put ENE, pentene. Tea time. Boy, does nomenclature work as thirsty work. But anyways, it's on the lead carbon is 2-pentene. But now notice each carbon has one of the same group or atom hydrogens. And they're both below. If I had a line like this, where the double bond is going across, or it's called a plane, both hydrogens are below. And that same side, we call that cis. Cis is same, trans is opposite. Now let's look at B, because I want to do A, C, and D first. And here we have a ring. Oh, Dr. White, Mother Nature loves rings. And here, how many carbons in the ring? I'll count the bends, 6. Don't forget the word prefix cyclo. Students do that in test 1 and lose points they shouldn't. I'm telling you that so you don't do it. Now, as cyclohexane, I have a double bond, drop the ANE ending, put cyclohexene. When there are no other functional groups in the molecule, and this class there won't be, one of the carbons, everybody knows, has to be 1, the others 2, and it's going to be cis, so we don't put that there. Now, we have a methyl group and an ethyl group. And notice if one of the carbons is 1, the other 2, and to do it in the order to get the lowest number, it would be methyl group on carbon 1, ethyl group on 3. So it'd be 3-ethyl, 1-methyl, cyclohexene. Now, if you would put down in the test 1-methyl, 3-ethyl, don't tell the Iupac police, but I would mark that correct. I'm not holding you to the alphabetical rule. All right, let's move on to problem number 2. And here's the other type of nomenclature question. And this is, draw the condensed structure for the following Iupac names of molecules. And if we look at cyclohexene, and I put the double bond there, you could put it between any other carbon. All you're doing is rotating the ring around. And it's a 6-membered ring. How do you know what to do? You start from the right and go left. ENE ending, double bond. If that were ANE, cyclohexane, and between any 2 carbons on the ring, I have a double bond. Next, cis-butene. How do you start? From the right, move left. ENE ending, double bond. ANE ending, butane, 4 carbons. Notice the double bond starts at carbon 2, and it's cis. So it doesn't matter which way with this I start counting. I go 1, 2, my double bond. Notice both hydrogens are on the same side, cis. Now, this is important. You need to show the stereochemistry. Notice I have the methyl groups going up and the hydrogens down. That's 120-degree bond angle. All right, let's look at C. And how do we decode this to know what to draw? You start from the right, move left. ENE ending, double bond. Octene, that were ANE, octane, 8 carbons. Where's the double bond? Starts at carbon 3, and it's trans. So 1, 2, 3, 4. Trans means the hydrogens are opposite. For this class, hydrogens could be other things too, but I'm going to keep it simple for you. then 5, 6, 7, 8. And next we have methyl. Oh, I know that's CH3. Di means 2. Tri means 3. This is di, so that's 2. And they're on carbons 5 and 6. And here we go. And don't forget there are 4 bonds to carbon. Time out for a commercial from, or I should say, public service announcement from Dr. White. Your friend on test number 1 and 2 and 3 and 4, and the final is anything you draw, make sure there are only 4 bonds to carbon. 4. 1, 2, 3, hidden over here is 4. And that will help you. I can say on all the tests I grade in final, 60% of the wrong answers. If the student had discounted the bonds to carbon 4, they would have known, well, that can't be right. I've seen 3, 5. One time I saw 6, and oh, I almost fell off my office chair laughing. Don't do it. It's wrong. It will always be wrong. All right. Now, on test number 2, test number 1, get ahead of myself. There will be 47 points on reactions. And all but one will be give the organic reaction product or products for following reactions. How do you do that? Well, you look at a molecule and look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention. I hope that got your attention like that. And here A, we have a double bond. What are we reacting with? Hydrogen and nickel. Here's the general reaction. Double bond, hydrogen, a catalyst. I didn't write down the catalyst can be nickel, platinum, or palladium. Yeah, Dr. White. And you break the pi bond. Remember, double bond has, let's do this. Double bond has 1 pi bond and 1 sigma bond. Just to remind you, a triple bond has 2 pi bonds and 1 sigma. And just in case you forgot, each line or each bond, which you should know, is 2 electrons. So a pi bond here would have 2 electrons, a sigma would have 2 electrons. Here, 2 pi bonds, 2 times 2 is 4 electrons, sigma 1 electron. And you should know any covalent, which is all we'll talk about, chemical bond involves 2 electrons being shared as a pair. All right, if we look at B, double bond, on a ring, we don't show hydrogens. And the other friend you should have on test 1, 2, and 3, and 4, and the final, do we break carbon-carbon single bonds? And the answer to that is no, you don't break carbon-carbon single bond. No, 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 no. So remember that, it will also be your friend. And once I started teaching that after the first time I taught organic, grades went zooming high because students break bonds. Well, I'll break that, and it would always be wrong. All right, now we break the pi bond, and again, same general reaction. I mentioned this before, but some of my best students, I'll get to your question in a second, Danielle. Some of my best students, under each question like that, they have written the general reaction, and some of my best students don't, but they know it. Danielle, you had a question.
Yeah, on 3A, shouldn't there be a hydrogen going on the second and the third bond to carbon, or no?
On 3A.
Yeah, shouldn't we have drawn a hydrogen coming off of
Oh,
the
all right,
second and third.
all right. I did something on that one, which I shouldn't have done because I've been training you. Let's do it again. I'll show you the two answers that are acceptable. And that's a very good question. Thank you.
Okay.
Okay, first of all, look at. All right. I forgot whether it was 1 or 2 butane. No, I know. I think I had nickel as a catalyst and the general reaction. Now I'll write it down to remind you. And where's the double bond? These two carbons, you break carbon-carbon single bonds. And I broke the pi bond though. Don't forget this is 1 pi bond and 1 sigma bond. You don't break sigma or single bonds. And then you could write it this way. Remember, there are 4 bonds to carbon, so I'll put in the rest of the hydrogens. And what I did, which I normally don't do, is take this hydrogen, move it up there. Same thing here. This is one way you could write it. Notice CH3, 1 plus 1 is 2. Next one, the same thing. These are identical. I'm just showing the hydrogens. On the answer key, normally I write it this way. Whenever I did that answer key, I wasn't thinking. I did the way I did it. And it confused you. And all I can say is, I'm sorry, bad Dr. White, bad Dr. White. All right. And by the way, as you just learned, it's a good thing to ask questions because there's no such thing as a dumb question. Does that help you, Danielle? Okay, good. Let's see if I did anything else to confuse people. Hopefully I didn't. All right, let's look at C and D. Let's look at D because I've done chemistry instructor's favorite trick on a test. I've got a big, scary molecule. But if you look at there and say, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? All I see is a double bond. Everything else comes along for the ride. And what are we reacting with? Bromine gas, Br2. Double bond, halogen. I didn't write down, gosh, I was lazy for this one. X can be fluorine, chlorine, bromine, or iodide. To break the pi bond, each carbon double bond gets a halogen. And which are the 2 carbons? And let me do one thing. Hold it, hang in there. That's a little better. What are the 2 carbons of the double bond? These 2. And each one gets a halogen. The halogen is bromine. And that's how you do it. Now, again, I have been training you, and you should train yourself. Look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen. That's where the fun is. And that's where things are going to change. And the rest of that is just coming along for the ride. But if you don't know what to look for, ooh, that's scary and you get confused. You shouldn't. All right, let's look at E. E, I'm reacting what? A double bond. Remember, you can put reactants above the arrow like I've done here with HBr. Br is a halogen, X, and for this reaction, X can be chlorine, bromine, or iodine. In this case, it's bromine. Double bond, break the pi bond. 1 carbon gets H, the other gets X from the HX, which, well, it follows Markovnikov's rule. The carbon with the most hydrogens in the double bond gets the hydrogen, the other gets the halogen. As I got taught eons ago, The rich get richer and the poor get poorer, and we're talking about hydrogens. This carbon double bond has 2. This one has 1. Time to use your high-level math skills for my class, which is the larger number. Hopefully you all pick 2. So the hydrogen goes to this carbon, the bromine goes there. Do you break carbon-carbon single bonds? No. So you have 1, 2, 3 across. I have 3 across. The bromine counts as a bond to carbon, so I know how to put in my hydrogens. You could have written the first one as CH3, which luckily I didn't, so I didn't confuse you. Now, if we look at F, and I'm going to write it out because I was lazy when I did this. Hold on. HI. That's not what I want. There we are. All right, again, look at this and say, ooh, what's different? Double bond. Everything else is coming along for the ride. What am I reacting it with? HX, remember X can be chlorine, bromine, or iodine, the halogens except for fluorine. And you break the pi bond, remember 1 pi bond, 1 sigma bond, and 1 carbon gets H and the other gets X, and it follows Markov-Nikov's rule. The carbon of a double bond that has the most hydrogens gets the hydrogen, the other carbon gets the halogen. Oh, you don't put hydrogens on a ring. Let's look at these 2 carbons. And the question is, how many hydrogens are there? Well, there's 4 bonds to carbon. You notice this carbon right here has 1, 2, 3 bonds. So if I did put a hydrogen, how many would it have? 1. Now, if we look at the other carbon right here, how many bonds does that have? Remember, double bond counts as a 2. Don't forget this methyl, 3, 4. 4 minus 4 is 0. Which one of those is the larger number? Hopefully you pick 1. So what does that mean? First of all, do you break carbon-carbon single bonds? No. So I'm still going to have the methyl group. Still going to have the isopropyl group. Just think about it. 6 months ago, if I had said methyl, would you know what I'm talking about? How about isopropyl? Doesn't that feel good? You're learning? And it's not painful, I hope. All right, now I broke the pi bond, and this carbon has 1 hydrogen. The bottom one has 0. Where does the hydrogen go? Up here. Where does the halogen go? Right here. Now, since I don't show hydrogens, I'm done. Because if we look at this carbon, how many hydrogens does it now have? Well, 2 bonds, 4 minus 2 equals 2. So it went from having 1 to now having 2 hydrogens. So you did have a hydrogen there. And by the way, Dr. White and Mother Nature love rings, students don't. This is one of the reasons. I'm being honest with you. I always am honest with you. Now, if we look at G, what are we reacting? A double bond with acid. H plus is the way organic chemists show acid catalyst. Catalyst, something that makes a reaction go faster, but it's not consumed or added to the molecule. And we have water. And think of water as H and OH. OH is all I'll teach you later. I mentioned it, but I'll do more next in the alcohol chapter. Hydroxyl group. Break the pi bond, 1 carbon gets H from the water, the other gets the hydroxyl group OH, follows Markov-Nikov's rule. The carbon with the most hydrogens gets the hydrogen from water. The carbon removes hydrogens in double bond, and the other carbon gets the hydroxyl group, OH. This is 2, this is 1, what's greater number? And time's up, hopefully I'll pick 2. And the hydrogen goes to this carbon. You break carbon-carbon single bonds, started with 3, end up with 3, and the other carbon gets the hydroxyl group. Now, just so you know, it's important where you put things you're adding to molecules, which carbon. If you put the hydrogen on the middle and the hydroxyl group on the end, I'd mark it wrong 0 points. Why? Because you show me you didn't know about Cost rule or understand how to use it. And if we look at H, same thing, we got a ring, top carbon of the double bond has 1 hydrogen, the bottom has 0. Hydrogen goes top, hydroxyl group goes to this carbon. All right, any questions on double bonds? Anybody happen to look at a carrot or a tomato that's red and think, ooh, that's due to double bonds? All right, I got to work on you people to think about organic chemistry. I've got the rest of the semester to keep this up, and I won't give up. All right, let's move on to triple bonds. Triple bonds, alkynes, give the Iupac, and notice I'm asking Iupac, not common, name for the following. And the simplest alkyne, 2 carbons, triple bond, you take and name it as an alkane, ethane, drop the A-N-E ending, and put Y-N-E. Since I can't have the double bond any other position, I don't have to put a 1 in there because you can't have 2 ethine because there's only 2 carbons to put a double triple bond through. All right, now if we look at B, we have this molecule. And here, what's different? Ooh, triple bond. How many carbons in the longest chain with both carbons of the triple bond? Let's count. 1, 2, 3, 4, 5. Pentane. Drop the A-N-E ending, put Y-N-E because triple bond. What carbon of the triple bond is closest to the end of the chain? That's the side 1. So it's when, oh yeah, I better readjust my jaw. 1 pentyne. You cannot have sister trans with a triple bond. And I have never, I think once decades ago, I saw somebody do a paper. It's one of those papers like, look how cool I am. It's not really germane to helping advance chemistry, organic chemistry, where they had a super huge ring. I think it had a triple bond, but anyways. Let's move on to D, because D was my little joke on you, see if you fell for the trick. And you looked at there and said, oh, I see a T-butyl group. And there are 4 carbons, the T-butyl group is on the end. Wrong. You count all the carbons that are longest chain, including the triple bond. And this is 1, 2, 3, 4, 5, 6. 6 is hexane, alkane. But since I have a triple bond, I'll drop the Y-N-E ending, A-N-E ending, and put Y-N-E. I do that a lot of times. My brain gets ahead of my mouth and says the wrong thing, or vice versa, whatever. But anyway, it says hexine. Which carbon of the triple bond is closest to the end, and at the same time allows you to give the alkyl substituents the lowest numbers. Let me repeat that again in slow motion. Find the longest chain and count it in such a way that the lead carbon of the triple bond has the lowest number, but also, if possible, if there's a choice, make sure also that the alkyl groups have the lowest number. If I start from this side, the lead carbon of the triple bond is 3 and the alkyl groups are in carbon 2. If I start on this side, 1, 2, 3, it's still 3, but these would now be on 5. So the way I have it done is correct. And let's look at this. Longest chain 6, hexyne, lead carbon triple bond 3, 3 hexyne. Notice I have left over here and here, not 1, but 2 methyls. How do we say 2 in organic? Di. So it's dimethyl. Even though they're on the same carbon, when you see di in a name, you'll need 2 numbers, even if they're on the same carbon, which is why I have 2,2-dimethyl 3-hexyne. Now, let's look at the other type of nomenclature question. That's draw the condensed structure for the following Iupac name. And here I give you a common name. And acetylene is the simplest alkyne, 2 carbons with a triple bond. Now I have it drawn this way. And this is called left justified. I'm not going to spend the next 2 minutes saying if I spelled justify right, which I couldn't miss. You can also have, when the N carbon has hydrogens on the left, you can have right justified. And you can do that with a methyl group too. My software likes to do this. If I forget to override it, it will. Usually I don't, but not always. Sometimes my brain doesn't do it. Which one of these are correct? Both are. Excuse me. All right, let's go back. And let's look at D. How do you determine what to draw? Start from the right, move left. Y-N-E ending, triple bond. That were A-N-E, no name, 9 carbons. So I have my 9 carbons. And where's the triple bond? First carbon, carbon 2. Then I have on carbon 5 a methyl. This is 2, this is 3, 4, 5. And carbon 4, an isopropyl. And that's how you do it. All right, now let's do some reactions. Let's look at A. Look at a molecule and look for what's not a carbon-carbon single bond or carbon or hydrogen atom. And that should, I have to throw that in today, get your attention. I have a triple bond. I ignore the rest. I'm reacting with hydrogen. What's this bracket? XS, close bracket. That's organic chemist shorthand for excess. That means you have all the hydrogen in the world that will, anything that will react can. And that's so we don't have to balance it because organic chemists are lazy. Here we have catalysts. I forgot to put down platinum, palladium, or nickel. Break to not 1, but 2 pi bonds. And for each pi bond, each carbon gets a hydrogen. For 2 pi bonds, each carbon of the triple bond gets 4 hydrogens. You break carbon-carbon single bond. Oh no, don't look. There's a undressed carbon there. Oh, sorry. This should be CH3, then the 2 hydrogens, then the last one, HH and C. Oh, did I mess up? That's missing. And Vivian, you have a question? Go for it.
Yeah, while I was doing this, the acetylene, I had it as HC triple bond CH. Is that considered correct?
If you did what?
While I was doing this, the acetylene, I had it as HC triple bond CH. Is that also correct?
H,
C triple bond CH. But I never had the hyphen between H and C. I just HC.
Oh, you know, I see what
CH.
you're saying.
Yes.
That would be correct.
Okay,
I put lines in between hydrogen and carbon and other things to make sure I am doing it straight. If we were on a whiteboard and I had a long molecule, I'm drawing it without the lines, my structures start going toward the ground. Don't ask me why. When I put in lines, especially hydrogen, it stays straight. Now you do have to do this, put in the triple bond, but that would be correct. And you've got everybody else online right now watching this,
thank you,
our witnesses, that I said that would be correct.
thank you.
One thing to all of you, when I grade a test, I don't sit there and say, ooh, how many points can I take away from a student? No, I think, I hope they get it right. I hope they get it right. But if you get it wrong, I will mark it wrong. But I'm not going to nitpick if this is off by a little. But if it's wrong, it's going to be marked wrong. But I hope you do it right. Please, makes me happy to see students succeed. It really does. And thank you for your question. All right, now on the problem set, I forgot to put the catalyst for B. I put down platinum. And same thing, you break the 2 pi bonds. Each carbon of the triple bond gets 2 hydrogens. All right, let's look at C. Oh, let's do D instead. They're both the same. And here, what's different? Oh, a triple bond. Big scary molecule. And if you don't know what to look, it's big and scary and scares you. But if you know what to look, oh, it's just a triple bond. Reacting with chlorine gas excess. Here's the general reaction. Remember, you have 2 pi bonds. X2 halogen gas can be chlorine, bromine, and for this one, fluorine or iodine. And we have the bracket excess, closed bracket, because that means we have 2 pi bonds, and each carbon of the triple bond gets 2 halogens. In this case, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across. 1, 2, 3, 4, 5, 6 across. On the second to last carbon on the right, I have my 2 methyl groups, CH3, and my 2 carbons of the triple bond. I have broken both pi bonds. I didn't write it. And each one gets 2 chlorines, because that's what we're reacting. And you add a total of 4 chlorines. And that's the problem set for double and triple bonds. Any questions? All right, let's go back. Anything else in here? Nope, I can close this. Let's go back to aromatic compounds. And we went through halogenation, went through nitration, and let me remind you, this is the only reaction at all I can ask on test number 1, because I'm not teaching you directors. When there's something on the ring, what do? So remember, nitric and sulfuric, you put an NO2, not NO3. It's a common mistake on test number 1. I mark it wrong. Should be a nitro group is NO2. And sulfuric or sulfonation, sulfur trioxide, sulfuric acid. This is the only one I can ask, because I'm not going to put a director something on the ring, because I'm not asking to learn that. We're 2 semesters, I'd be teaching that, but I also have twice as long. I don't. So remember, there's also a hydrogen there. Students write SO3, and that's wrong. Don't forget that hydrogen. It's totally different molecule. Well, the other one, I don't think SO3 alone even can be exist in nature for our life. And finally, I talked about Frito Craft's alkylation. It's named after the 2, I believe, British chemists who came up with take a benzene ring, react it with an alkyl halide, or X for most intents purposes, chlorine and bromine, and you need aluminum trihalide. You replace one of the hydrogens with the R group. The bond from the benzene ring goes to the carbon with the halogen in the R group original. And you get HX, but you don't have to put that down because I'll just ask what's the organic product or product. And this is something very special. This is a reaction where we make a carbon-carbon single bond. And that's very rare. Well, all the hundreds of general reactions I know, and there are a lot more I don't know, there's only a handful, like about 20 reactions, very small amount, where you can make a carbon-carbon single bond. So let's have some fun with this. What would be the two product starting materials I would react with aluminum tribromide to make this compound? And since you might not have memorized it yet, I'm going to help you out on the test. You won't have this help. The fun part of organic chemistry, synthesis. But then I'm biased. I'm a synthetic organic chemist. My training is how to make molecules. Remember, this is the fun part. I say fun enough, you'll believe me. It's true. All right, I think everybody's done. So let's take a look at this. We look at the product we're making right here. What's different? Oh, I got a benzene ring, but there's something on here. And what is that? An alkyl group. Remember, R means something just with carbon and hydrogens. There's no other functional group there. And what are we reacting with? Aluminum trihalide. Remember X here, I should have written chlorine or bromine. And that's Frito Craft's alkylation. Because what two things do you start with? One of them was benzene. Don't forget to put the lines in front in there or a circle, otherwise that's cyclohexane, and I mark it wrong. What's my R group? 3 carbons. Which carbon is bonded to the benzene ring? The center one. So which one will have the halogen? The center one. What is it? Bromine. And I know there are 4 bonds to carbon, so I can do this. Now, on a test, you have to write all this? No. What you do have to do is write that and that. If you want to, you can put a plus there. If you don't want to, that's okay with me. And that's how you do it. If you look at this benzene ring is going to bond to the carbon with the halogen that leaves, and you would get this product. And it works. Speaking about working, oh no, I've gone a whole minute into our break time. I'm not going to cheat you out of any break time. Also, I got to get up and stretch. And I'll see you in 5 minutes. What time is it? I'll see you at 1:56. Be back in 5. Time to get going. I was just thinking, do you ever play hide and seek? Come out wherever you are. I hadn't thought of that in a long time. All right, before I get moving on, in the aromatic chapter, I got a question for you. If you don't feel like answering it now, shoot me an email. Is the time I have right now on Monday and Wednesday from 5 to 6:15 for my office hours, that a time you can come to? Now, I'm going to always have office hours on Monday and Wednesday. That's convenient for me, I'm being honest. However, I can adjust it a little later if it would help people out. So if you think, if I say start instead of 5, like 6 to 7:15, let me know, and I can always adjust it. I've got that power to do so. And if we were face to face, I always have my office hour, an hour and 15 minutes after the class. And that was before we used Zoom. And if you can't make it, well, I'm not there on Tuesday, Thursday, or Friday, Saturday, or Sunday. Well, that's it. With Zoom, I can adjust that so it helps you out. So if you would like to see a different time, let me know by email. Or you can say it now, up to you. All right, we're talking about aromatic compounds. Let's talk about polyaromatic hydrocarbons. Remember, a hydrocarbon is a molecule with only carbon-hydrogen atoms. Benzene is a hydrocarbon, and it's aromatic. And polycyclic means poly in organic means many, and cyclic, means rings. That reminds me, unfortunately, about a year, almost a year now, very nice woman who used to be the Dean of English at ECC, passed away, Polly Nash, very nice woman. I got to meet her through mutual friends and meet her and her partner. But anyways, first time I met her, oh, I'm Polly, or somebody. I said, oh, do you know your name means many? And she gave me that kind of look like, how many million times I heard that? And she had. But anyways, everybody watch, click the switch. Will this be on a test or a final is off? But I'd still like to talk about it. Now, polycyclic aromatic hydrocarbons, those are aromatic carbons with more than one ring. Now, I haven't talked about it, but you can have rings connect together. We call those fused rings. And a very common or well-known polycyclic aromatic hydrocarbon is naphthalene. And this is the structure of naphthalene. Notice the two rings share two carbons. That's what we mean by a fused ring. They're connected together. And if you count the number of pi bonds, there's 2n plus 2 pi bonds. And they're all conjugated, alternating single, double, single, double, single, double. Even though I'll never ask you what conjugated means on a test or final, I will use it in class like I just did. Now, unfortunately, we're not going to be face-to-face with our labs or our lecture, which I think now is a safe thing, even though some schools are cutting back. And I don't know if the governor is going to announce it too, that Illinois is going to cut back on wearing a mask, which I think is wrong. We're not done with COVID. I hope I'm wrong, but I don't think so. But anyways, if you smell naphthalene, it's got a very characteristic odor to it. And what's its main use? It's used in mothballs. And mothballs are just naphthalene is a white solid at room temperature, and you can press them into little balls. And back when I was a kid, my grandparents had a couple of drawers with wool stuff that they threw in mothballs. You could smell it. Now, when we moved into a house when I was about 10 in Lincolnwood, where my parents bought a home, we had one cedar closet that's supposed to keep moths away, but my mother still threw mothballs in there so they wouldn't eat your wall. I don't know, do moths still do that? People still use mothballs? Don't know. Ooh, I just thought of something. Hang in there. Mothballs for mice? What the heck? And the answer is they do. You can get them at Walmart, Walgreens, even on Amazon. So anyways, and if you can see there, same company, I think all of these, they're those spheres, they're about this big. And for some reason, moths don't like the smell of that. Doesn't kill them, just keeps them away. Now, another very important polycyclic aromatic compound is graphite. Now, graphite exists as large sheets of polyatomic six-membered rings connected together, piled one on top of each other. Remember, the switch is off. They don't show the double bonds, but each one of these rings is 6 rings, and they're not different colored. They're piled on each other like if you had a stack of paper. Now, to separate this way is very easy. To pull the rings apart in the sheet is very hard. It's very strong. Now, where do we use graphite? Well, one is a lubricant. The other is in pencils, lead pencils like this. Hold on. Everybody see the lead, the tip focus. Oh, better. There you see them. Those rods are graphite with some other material, but mainly graphite. And when you write, hang in there, it's a special demonstration. When you write like that, what you're leaving is sheets of graphite on the paper. And that's why you can see a line. But you didn't know that was organic chemistry. Yep, it's everywhere. Now, interesting thing, graphite is very easy. Like if this were 2 pieces of paper on top, separated that way, but pulling it this way is quite strong, actually stronger than steel, and it's a lot lighter. So guess what happened? Back, it's a couple of years ago, back about 1995, 1996, one chemist in Texas, one chemist in Japan, I can't remember the Japanese chemist, I believe that chemist in Texas was Smalley, both independently came up at the same time to make what's nanotubes. And nanotubes is where you take graphite sheets and can make them into a, hold on while I get this, a tube. And you get a tube like this of the graphite sheet, and they found a way to do it. Turns out nanotubes, nano means a billionth of a meter, which is much smaller, much smaller in diameter of my hair, what's left of it, or your hair. And it's very strong. You put those in things. Now, since then, they've found other ways of making them, but since 95, 96, governments of the world have been spending billions on nanotechnology and research. Because if you can make things out of nanotubes, it's much lighter and it's much stronger, almost as strong as steel, which means if you're building a car or plane out of that, guess what? It's less gas being consumed and you need less energy to make it move. Now, a very, I want to say about 2005, give or take a year or two, oh, excuse me, a couple of very creative chemists found a way. Graphite is sheets on top of each other. Oh, each sheet is called graphene. This won't be on the test. And everybody said, well, you can't separate those sheets. Nobody's been able to do it. Well, they found a way to separate it and make individual sheets out of graphene. And for that, they won the Nobel Prize, which they deserved it. How did they do it? They used an old crystallographer's trick to get a single sheet of something. They took some graphite, put in some Scotch tape, and very carefully pulled it off. Then put the Scotch tape into a solvent that the tape is backing and the glue was dissolved, and floating around in there were sheets of graphene. And those are very strong. And there's a tremendous amount of research. How can you make bulk amounts? When I say bulk, I'm talking about millions of pounds a year economically. And that's going to be, when they figure that out totally, they're pretty close, will change our world. And I want to talk about that. Everything on polyatomic, polycyclic, aromatic, hydrocarbons will not be on the test. All right. I have covered everything for test number 1. And why did I do that? I don't know. Test number 1. And this Monday, I will go through I'll go through the aromatic chapter problem set on Monday. I will also do my world famous review for the next test, which in this case is number 1. Got that right. See, I'm ambidextrous. I can do it both. I am ambidextrous. But anyways, I will also on Monday do my world famous review for next test. Students say it helps them do good on tests. So guess what? I'm going to do it, and I will. And with that, do you know what time it is? It's new chapter time. Now, this new chapter will not be on test number 1. It's going to be on test number 2, but you'll see throughout the semester, I'll finish early material like I am now. And this gives you a chance to study for the test, as opposed to like Monday finishing up, I could have done it this week, aromatic compounds, and giving you a test today. That's not fair. You wouldn't have time to study well and practice, which means you wouldn't have done well as you could by having extra time. All right, what's that new chapter? Well, this is going to be an interesting one. There's stuff in there I'm going to cover. A lot of stuff I'll cover. He's really going to do that. And one thing I will have to warn you about, there's something in this chapter I'll talk about that if you consume too much of it, you'll get inebriated, which you shouldn't. Well, you shouldn't, especially when you're driving. You should never drive and drink. All right, what's that new chapter? And that new chapter is alcohols, phenols, and thiols. Now, some people pronounce this phenols. No, that's wrong. It should be phenols. Oh, I have to warn you. Part of this chapter is going to be, I have to say this, real stinky. I mean, really stinky. So we'll get into that too. What's an alcohol? Well, an alcohol has the general formula ROH. And that means a molecule that has a carbon and hydrogens, one of the carbons, and it can be more than one, has an oxygen hydrogen, which we call hydroxyl group. This is an alcohol. Now, these next couple of chapters, like I did this alkenes, alkynes, and aromatic compounds, I'm going to introduce you to new functional groups. So everybody say hello to the alcohol group. And we'll do Iupac nomenclature. And then also, where do you find this in your daily life? And I'll talk about how to name it, how to draw structures from the name, and then the fun part, how to make it, and also how to react it. That's the real fun part. So An alcohol is carbons with a hydroxyl group, OH. Now, hydroxyl group OH is not a functional group, but when it's on a carbon, it can be an alcohol. It can also be other functional group that we'll learn later in the semester. But when a hydroxyl group is on a carbon, nothing else, we call that an alcohol. Well, let's look at an alcohol. And now it really starts coming into play. Look at a molecule and look for what's not a carbon or hydrogen. And oh, look, there's an oxygen here with a hydrogen. That's a hydroxyl group. It's on a carbon. This is an alcohol. And the question is, how do you name it? What are the Iupac rules for that? And let's go through that. Had too many things open. I had to close something. All right, everybody see nomenclature alcohols on your screen. Thumbs up, people. Thank you. All right, the hydroxyl group OH in alcohols is indicated. How do you do that? You've changed the A on the ending of the longest carbon chain with the hydroxyl group to OL ending, OANOL. In other words, you drop the E and add OL. For an alcohol, you name the molecule with the longest chain that contains the carbon with the hydroxyl group on it, name it as an alkane, and then drop the E, and for alcohol, we use OL ending. You use a number to denote the carbon the hydroxyl group is on. That has priority over alkyl groups, and therefore it gets a lower number. The rest of the Iupac rules are followed, except the hydroxyl group has priority in numbering, gets the lowest number. Seed board for examples. Nobody's looking at the book, so let's get to work. What do we have here? Hydroxyl group on a carbon. It's an alcohol. How many carbons are in the longest chain? Don't know. 1, 2, 3, 4. Well, I know that's butane. I'll drop the E, and for an alcohol, add OL. Remember ROH, alcohol. And now am I done? No, which carbon is the hydroxyl group of the alcohol on? You number it from the side to give that always the lowest number. And notice if I call this 1, this is 2, if I go the other way, it would be 3. Which is smaller, 2 or 3? Time's up, hopefully all. And that's 2-butanol. And I'm done. And that's how you do alcohol. Oh, let's do another one. And the hydroxyl group counts as 1 bond to carbon. Now I'll do this one, then I'm going to share. And the question is, what's the Iupac name? And I look at that. Now I'm going to look for what's not carbon, what's not hydrogen, also what's not a carbon-carbon single bond. But in this chapter, all you got to do is look at for what's not carbon, what's not hydrogen. I said, ooh, an oxygen on with a hydrogen on a carbon, hydrox group on an R group, that's an alcohol. And how many carbons are in the longest chain with the hydrox carbon with the hydrox group? 1, 2, 3, 4, 5, 6. What do we call 6 carbons? Hopefully all know for test number 1 and 2, 3, 4, and the final. That's hexane. But it's an alcohol, so I drop the E at the end of hexane and add OL. OL ending alcohol. And what carbon is that hydroxyl group on? Well, this way is carbon 3. If I numbered it the other way, it'd be carbon 4. So the answer is carbon 3. So that's 3-hexanol. As soon as I say 3-hexanol, that's all spoken for. Am I done? No, it's your old friend, the methyl group. Say hello. Hello. Oh, awful humor Wednesday. So I have methyl. And what carbon is it on? Well, if this is 3, this is 2. So that would be 2-methyl 3-hexanol. Let's go through what I did. And you find the longest chain with the hydroxyl group OH. And you name that as an alkane, 6 carbons, hexane. Drop the E and replace it with OL. That tells you it's an alcohol, hexanol. What carbon is the hydroxyl group on? And it's 3, so it's 3-hexanol. And are we done? No, we had our old friend, the methyl group, and it's on carbon 2. And that's how you do it. Oh, I better let you have some fun. And I'll ask you, what's the Iupac name for that molecule? 3 points each. Remember, Iupac means the official name, even though I like to say International Union of Pure Applied Chemistry, because I think it's cool to say. And if you finish early, give me a thumbs up or I'll send a poll out too. I see one person done. Doesn't it feel good to understand this stuff? Oh, 2 people. The thumbs are coming in. All right, I better shoot the poll out just to check. Well, I think everybody's done, so I better get to work. So if I look at this molecule, do I see something that's not carbon or hydrogen? The answer is yes. Oxygen with a hydrogen hydroxyl group. That's an alcohol. And how do we name that? We find the longest chain with the hydrox group, the alcohol group. That's 1, 2, 3, 4, 5, 6, 7. And 7-carbon alkane is heptane. Drop the E ending. It's an alcohol, add OL. And then what carbon is it on? Carbon 1. And I'm done. And I'm going to share the fun some more. What's the Iupac name for that molecule? Remember, the longest chain has to include the carbon with the hydroxyl group on it. Oh, I gave it away. Well, I just looked at the clock. And time flies when you're having fun with alcohol. Oops. I shouldn't have said that. But anyways, let's take a look at this. How do you name this compound? You look for what's different, what's not a carbon or hydrogen. Oh, look, oxygen with a hydrogen, hydrox group on a carbon, that's an alcohol. And now, how many carbons in the longest chain? 1, 2, 3. If I come down here, it'd be 4, 5. But if I go across, it'd be 4, 5, 6, 7. So the longest chain is 7. That's heptane. It's an alcohol. So you drop the E, add OL, heptanol. What carbon is the hydrox group? We start from this end. It's on carbon 2. If I started from this end, it would be 1, 2, 3, 4, 5, 6. 2 is smaller than 6. So it's 2 heptanol. As soon as I say that, that's all spoken for. Are we done? No, there's something left over. What's 2 carbons? Hopefully you learned a 2 carbon alkyl group is ethyl. And what carbon is it on? Carbon 3, says 3 ethyl 2 heptanol. All right, now let me show you rings. We have this molecule. How do we do that? What's the longest chain? No, what's the ring? That would be 6 carbons, hexane, but it's a ring. Don't forget the cyclohexane. But it's an alcohol, and therefore drop the E, add OL. Now, if that's the only functional group in the molecule, not alkyl groups are not functional groups, the carbon with the hydroxyl group is always number 1. Everybody knows that, so we don't have to put a number, and I'm done. That's cyclohexanol. And when you're numbering a ring that has only a hydroxyl group and alkyl groups, which is what will happen in this class, you don't put number 1 because everybody knows that. Now, at my level, what if you have an alcohol and a double bond? The alcohol gets priority to the lower number, but I won't do that in this class. So, and alkyl groups are the same. And why don't you write the Iupac name for the following compound? Your turn. Oh, I keep on forgetting. Okay. All right, let's do this. And the question is, what's the Iupac name for the following? Is everybody done? I think so. We look for what's different. Ooh, an oxygen. What's not carbon? What's not hydrogen? Get your attention like that, or like this. Oh, that came out wrong. Let me do it again. That's better. All right. Carbon with a hydroxyl group, alcohol. It's on a ring. How many carbons in a ring? 6. As hexane, it's a ring. Don't forget the cyclo. Since it's an alcohol, you drop the E and add OL. Everybody knows it's number 1, so you don't put 1 cyclohexanol, can't have 2. And you number that way to give the other substituents the lowest numbers. And notice my favorite, a T-butyl group, if you want to write chert, that's all right too, is on carbon 3. So that's 3-T-butyl cyclohexanol. Oh, let's do one more. These are fun. And why don't you try this one right here? What would be the Iupac name for that molecule? Remember, you always number in a way to give the alkyl groups the lowest numbers possible. Ooh, I threw a tough one at you. Let's see if you're up to it. I hope you are. If not, you'll learn. If we were in a class, I'd ask, when you're done, look up and smile. And even if you didn't, I could look into the classroom, tell when everybody's done, because I like to give everyone time to finish. All right, I think everybody's done. Let's do this. All right, if I look at this molecule right here, I look for what's different. And I normally say what's not a carbon-carbon single bond, carbon or hydrogen atom. In this case, oh, an oxygen. That should get your attention. It got me with a hydrogen on a carbon. That's a hydroxyl group on a carbon, our group, and that's an alcohol. And how do we name it? We'll name the longest chain, or in this case, the ring that the hydroxyl group is on. 6 carbons. I should have done a 5-membered ring there. Sorry. I like 6-membered rings better than 5. And that's cyclohexane. but it's an alcohol, so I drop the E, add OL, cyclohexanol. This is carbon 1. Am I done? No, I have a methyl group and an ethyl group to take care of. And you number in a way to give those the lowest. And that's not clockwise, it's counterclockwise. And therefore the methyl group is on 2, the ethyl is on 3. So that would be 3-ethyl, 2-methyl. Yeah, I can fit it in. Sorry, that's the methyl. Cyclohexanol. Now, let's show you something. If I had called this 1 and gone the other way, the ethyl would be on carbon 5 and the methyl on 6. Which is smaller, 2 and 3 or 5 or 6? Time's up, hopefully I'll pick 2 and 3. And that's how you do. Here's the structure, draw, give the Iupac name. Now let's do the other type of nomenclature question. By the way, this is material for test 2, not test 1. But test 1 will have nomenclature problems and reactions and general knowledge. The point breakdown is a little different, but you should know how to do that. Oops. And I'll do this one first. And you're asked to draw 3-T-butyl, 2-T-butyl, 3-octanol. How do you do that? You start from the right and move left. OL ending, alcohol. And if that were an E, it would be octane. Octane is 8 carbons. Which carbon has the hydroxyl group? Carbon 3. Now listen up. When I learned organic chemistry, when I was an undergrad, my instructors, and even in grad school, and my professor always started from this side when counting. Now you can start from either side, but good habits I don't break. So I'm going to do, and on the answer keys that I put for problem sets, I'll call this 1, 2, 3. You could have also started from this side. That's correct, but I just don't. That's my preference. Most organic chemists don't ask me why I do that. So I have on carbon 3, a hydroxyl group, the OL ending, the alcohol, and then a T-butyl group on carbon 2. And I might have picked a bad example. There's another way. Yeah, I could have named this. Once in a while, I pick a bad example on the fly. I should have made that just a methyl group. Sorry, because that's not the true Iupac name, but that's how you draw it. And that's a mistake I make once in a while. Let's do another one, but I'll let you try this. And that's a good name. So draw the structure for 4-methyl 2-decanol. Oh, I made a mistake. Oh, I feel so embarrassed. Is my head face turning red? I better check to see if you're done. This is a good class that's got some. All right, come on, why won't you? There you go. I think everybody's done. By the way, if I'm not giving you enough time, let me know, shoot me an email or a chat message. How do you decode this to know what to draw? You start from the right and move left. OL ending. Alcohol. Hope none of you will have nightmares seeing me draw and say alcohol tonight. Anyways, if that were an decane, 10 carbons, I better get to work. I got a lot to do here. Draw. Ten carbons. Where is my hydroxyl group? On carbon 2. I'm going to start numbering this way. You could have done this way too, but I don't. And then on carbon 4 is our old friend, the methyl group. You know, there are 4 bonds to carbon. And we're done. Oh, let's do one more. Actually, 2 more. Here's the next one. Why don't you draw the structure for ethanol? And there's no number here because there are only 2 carbons, and whichever one you pick is always going to be carbon 1. Everybody knows that. I think next week I'm going to put out a message. It's International Turn on Your Webcam Week for Dr. White. Makes me feel better. And thanks to all of you who do turn on your webcam. All right, looks like everybody's done. OL ending. Alcohol. Two carbons, if that were ethane. And you can put it either down or across. I'm going to do it this way. It's so small of a molecule. You could have also written it this way. And this molecule, ethanol, is the molecule in beer, wine, and hard spirits, like my favorite vodka, that gets you inebriated if you drink too much. Norm, I'm not in any way suggesting you should do that, but my favorite vodka is either Grey Goose or Absolute. Dr. White loves his vodka. I'm not an alcoholic, but I do. I either drink it straight up or with ice cubes on the rocks with a couple of olives, my favorite. And if you want a good break and you have a Costco membership or know someone who does, they have two different types of vodka they sell. Their cheapest one, the American, nah, not that good. Now they have one that's they call it their French vodka. It's got red glass on the bottom of a very tall bottle, and it's quite reasonably priced, and it's almost identical to Grey Goose and Absolute, which is why I buy that. I don't buy Absolute or Grey Goose anymore because I can get that a lot cheaper at Costco, and I do. Let's do one more. And why don't you draw the structure for 2N-butyl cyclopentanol? Doesn't it feel good? You're getting the hang of this? Remember all the horror stories you heard about organic? They're not true. Or they are true with another instructor, not mine, not me. All right, let's do this. I think everybody's done, but I'll give you another 20 seconds. Go. Looking at a watch that has a second hand and a digital sign, seconds too. All right, let's do this. How do you decode this to know what to draw? Start from the right, move left. OL ending, alcohol. Hydroxyl group on a carbon, that's what R is. And this is, if this were an E instead of OL, be cyclopentanol, which is a 5-membered ring. And one of the carbons, most of you are going to put it up here. I might not, but you would, is cyclopentanol. Now, this is carbon 1, and there's an N-butyl group on carbon 2. Most of you are going to go clockwise, so I will. 4 carbons. And we have N-butyl cyclopentanol, and that's an alcohol. And when I look at the clock, it's time for a break. Let's take a 5-minute break, and I will see you at 2:50. I'll be back, and hopefully you will too. time to get going. Don't you like my collection of whistles? All right, we were talking about alcohols. Alcohols when you have an OH group hydroxyl on a carbon. And let's continue. And we went through the Iupac names. Now there's something called common names. And this is something you should know. And common names, I'll never ask you what's the definition of a common name, but you should know some key common names. They are key alcohols that the common name is more likely used than the Iupac name. And these common names are derived by naming the chain, the hydroxyl group on as an alkyl group, and then adding the word alcohol. Again, you have the chain that the hydroxyl group is on, and you name it not as long as chain, but as an alkyl group before alone, and then you add the word alcohol at the end. C board for ethyl alcohol, isopropyl alcohol, and butyl alcohol or T-butyl alcohol. Well, I better get to work. And these are three I'd like you to know. And let's go through and do this. All right, let's look at the first one. And here we have a hydroxyl group and a carbon, two carbons, ethane, and drop the E at OL, ethanol. However, if you look at a bottle of wine, my favorite is white German wines. I worked there, so that's like, we have what's this R group on the hydroxyl, and that's an ethyl. And therefore, the common name is ethyl. I don't have a room, so I'll write the rest of it down here. If I can spell. Ethyl alcohol. Hold on. I think I have a feather in my throat. I don't have any birds in the house, but I got it. And that's ethyl alcohol. And a number of products you buy, if you look at the ingredients, and wine is one of them, you'll see ethyl alcohol, not the ethanol. Now, if you happen to drive into a gas station and you look on the pump, it will say this gasoline contains up to 10% ethanol, which is in Northern Illinois. I think it's the rest of the country too. And that's the Iupac name. Now, let's look at the next column. And here, we look at this structure, I have 1, 2, 3 carbons, propane. There's a hydroxyl group on carbon 2. So the Iupac name is 2-propanol. Nobody calls it that. If I look at this structure, what's the R group on the hydroxyl group. What do you see there? An isopropyl group. And the Iupac, the common name would be isopropyl alcohol. And that's isopropyl alcohol. And there are two products you can get at just about any supermarket or anywhere, big box store. And that is if you take 70 to 90%, and they have both 70 and 90% isopropyl alcohol. And either 30 or for this one, 10% water, mix them together, you get a homogeneous solution that means the same throughout. And we call that rubbing alcohol. And at times that's been used to disinfect things. I bought it as soon as COVID started, when I realized what was happening, that isopropyl alcohol will kill them. I went out real quick before everybody else figured that out and got a couple bottles for my house, just in case I needed it. And I still have it just in case. Now, if we look at the last column, and you should know on the test, I'll never ask you what's the common name, but I will ask you, here's the common name. You should know how to draw the structure. Now, the last one right here, we've got a hydroxyl group on the carbon, 1, 2, 3 carbons, longest chain. That would be propane. It's an alcohol, propanol. The hydroxyl group is on carbon 2. And up here, we also have a methyl group. On carbon 2. Nobody ever calls this 2-methyl-2-propanol. All organic chemists, including Dr. White. We look at this structure, the R group attached to the hydroxyl. What is that? And that's a tertiary butyl group. And everybody in organic chemistry who knows anything calls it a T-butyl alcohol. I forgot to tell you, a couple of companies, and I still do it, if I'm talking to other organic chemists, I'll call isopropyl alcohol. We call this, and I'll never ask this on a test, IPA, short for isopropyl alcohol. And that's when you don't want to use acetone to clean glassware and something cheaper, use isopropyl alcohol. And a couple labs I worked at, we went through a lot. Anyways, you don't know what acetone is, I'll teach you that later on. You should know, if I asked on a test, draw the structure of ethyl alcohol, it's this structure. Draw the structure of isopropyl alcohol, it's either of these two. If I asked draw the structure of T-butyl alcohol, it's either of these two. By the way, for ethyl alcohol or ethanol, you could have also drawn the structure like this. All I'm doing is rotating at 180 degrees. Not bad. All right, any questions? Let's move on. Let me just close something. All right, let's move on. Now, let's look at this molecule, which you should know the structure of and its name. A benzene ring with a hydroxyl group is not called benzenol. No, because for eons, chemists before Iupac called the benzene ring with a hydroxyl group phenol. Some of you have heard it pronounced phenol. I worked for a company, we made or bought millions, a couple million pounds a week of this molecule. I used it in my last patent, and I had a running argument with the other chemists there. They called it phenol. I said, no, it's phenol. But anyways, and this is its name. So if I ask you, what's the Iupac name of that molecule? It's phenol. And derivatives are named as similar to toluene. And phenols are named with the hydrox group on the benzene is included in the name. So if I were to show you the following. If we have this hydroxyl group, it's on a benzene ring, that's phenol, that's the base name. Now it's disubstituted. This is 1, this is 2, this is 3.
We can't see it, Professor.
Oh no, I've been pretty good about that. Thank you for letting me know. What was I stuck on? Oh, I see what I did. I forgot to switch over. Thank you. That happens on Zoom. All right, now can you see it? All right, instant replay. Nomenclature of phenols. A benzene ring with a hydroxyl group is called phenol. Some people call it phenol. And derivatives are named just like as we did for toluene. So if I have this molecule, I have what's the base name, benzene ring with hydroxyl group, phenol. On carbon 3 is N-propyl. And since it's disubstituted, hydroxyl group counts as a substitution. 1,3 would be meta, and that's be meta and propylphenol. You had more groups on there, then you use numbers like I did for TNT. Now, I'm going to go and move forward, and I want to cover 2 more topics before we stop and have our lab for today. Now, can you see hydrogen bonding of alcohols on the screen? All right, switches off, click. But this is an important concept of alcohols you should be aware of. I won't ask it on a test. What's a hydrogen bond? Hopefully you remembered from your general chemistry. Water, which has hydrogens on an oxygen. The oxygen is more electronegative than the hydrogen. So when they're sharing a pair of electrons, the oxygen says, I'm bigger than you. I'm going to share a little closer to me. So this means, this is the Greek word letter delta, lowercase. This means small difference in chemistry. Now, delta, capital like this, oh, and it's an awful looking delta, means large difference or just difference. And I'll never ask that on test, but I will. Hope is a difference with an E or an A, whatever. You know what I'm talking about. If I had another water molecule, same thing happens. And opposites attract, and this charge, slight attraction, is a hydrogen bond. And that's the reason why water is a liquid at room temperature, not a gas, which changed how our planet would be. If it was a gas, we wouldn't exist the way we did. but luckily hydrogen bonding does. Now, in hydrogen bonding, that can be on nitrogen, oxygen, or fluorine that has a hydrogen atom. Well, alcohols have a hydrogen on oxygen. And the same thing happens here. If I had another alcohol, and I'll draw it this way, you can have hydrogen bonding. Now, this is not a true bond, but it has significant effects. And that means alcohols have higher boiling points than other alkanes, a similar molecular weight with oxygen, and they're soluble. And I'll teach you later in the semester what polar solvents mean. And oh, I don't know if I've used this before, but I tend to use this. IE means Latin for something, and let me learn how to write. Whenever you see IE, that means that is water. In this case, when I have water after IE. So alcohols can hydrogen bond to water, which means alcohols, the smaller molecular weight, are soluble in water. And public service announcement. Bartenders don't like being taught organic chemistry. You know, you can make that drink for me, which years ago I used to drink a lot of Canadian Club and 7-Up, otherwise known as CC and 7. 7-Up is mainly water with some sugar and flavoring, and I like. I also now really Vernors I love. Anyways, I say, you know, you can mix those two together and they're homogeneous because of hydrogen bonding. I get a look like, do you have too much to drink tonight already? But anyways, probably did if I'm talking organic chemistry in a bar, but that's because of hydrogen bonding. All right, now, again, switches off, click the acidity of alcohols and phenols. Remember, acidity means the ability to donate a proton. I'll never ask you that an acid can donate protons. Alcohols are very weak acids, but their conjugate bases, what you form, are very strong. And what does that mean? Again, switches off. Here, the equilibrium only is here, but if you form this is the conjugate base. This is a very strong base, and this won't be on a test ever. And these are weak alcohols, or acids, I should say. So the equilibrium stays mainly this side, but if you do form any, or if you use this type of compound, which we will later on, it's a very strong base. Now, phenol is a weak acid, but it's much stronger than regular alcohols. And let me show you, this is totally off, will not be on test, but Dr. White's going to have some fun. Something I haven't done before. Well, I can draw resonance forms. Resonance, when you're just moving electrons, if I move these electrons here, these have to move, and this will never be on a test, but I'm having Dr. White fun. I can draw another one by moving the electrons here. Double-headed arrow shows you. And there's another one. And when you can draw resonance forms, you make something more stable. So this is called the phenoxide ion. It won't be in this test. And that's more stable than this anion. And in my last patent, I actually used phenoxide anions, so I know them quite well. I'm actually a world authority on them. Now, switch is still off. Alcohols can be bases. Bases is a proton acceptor. Base plus a proton, you form a salt, like this. And bases accept protons, like hydroxide. Well, alcohols are weak bases. They can be protonated. That means you can add H plus to it. And they react with strong acids. Base accepts it. And this is the first step in two important reactions I'll teach you. What does that mean? Again, this will not be on a test, but if I take an alcohol and react it with an acid, these electrons will act as a base. And you get this intermediate that can't be isolated, which is why I put the brackets there. Does somebody see something similar or something familiar in that molecule? Two hydrogens and oxygen. Two hydrogens, I can't think, what does that look like? Hold on, I have some water. And guess what you see, or should, this right here. And why is that important? Because in a couple reactions I'll show you, you lose water and you're left with this, which is called a carbonium ion, which is very reactive. And whenever you can lose a stable group, and trust me, or molecule, water is very stable. It happens. And that's because alcohol is a very weak base and will react stuff with acid. Well, this is a good time, I think, for us to get ready for the lab. Let me close some things first. Let me check something out. All right, I think I closed it quick enough. It's time for a lab. And today's lab deals with alkanes and alkenes, double bonds and single bonds, and they're hydrocarbons. And when I inherited this class, the way I looked at the labs, and they were pathetic. They were awful. I challenged myself. One of the challenges, and I think I mentioned this before, I can't use a normal lab book because as ECC, when I inherited this class, and I haven't changed it for reasons I'm not going to go into, we have an hour and 50 minutes, approximately 2 hours, actually less than 2 hours, where other schools in the area, like it's about all of them, this class would have a 2 hour and 50 minute, almost 3 hour lab. So I have to have shorter labs, educational, and use very little money. And I came up with my own labs. And what I do is expose you, the student, to some basic things about chemicals you probably never will handle or think about again the rest of your life, because most of you, like all of you, aren't going to become organic chemists. That's okay. We established that the first day. I know that. And now you know I know that. Don't forget, the lab we did last week is due today, but you have up to a week later to get it in, but get it in on time as soon as possible. And this is available on D2L in the assignment area. To download this lab as either a PDF file or a Word document. Now, if we are face to face, hydrocarbons are flammable. In an organic lab, you never light a match or a Bunsen burner because you'll have a fire. And I would teach you where to dispose of everything. We'd have special waste bottles. Nothing goes down the sink. All right, first one is odors. And I'd have set up a series of chemicals. If they were liquid, we have 2x2, and Dr. Daly, who manages the lab when we work for face to face, actually, when I first started, he wasn't hired there, and I'd have students tear up some piece of paper towel. Once he got involved, he was amazing. It is amazing. He had cut from my lab 2x2-inch paper towels. You put a few drops on it. Now, when you're smelling a chemical, you never put the bottle under your nose. That's dangerous. You go like this to get a little whiff of it. And that's what you would do. Now, since we're not in a lab, and I don't want you to have these chemicals at home, I've given you the type of smell that the students would put down. Now, notice in red here, part of today's lab that you'll hand it next week, says draw structures underneath the name. So for hexane, octane, and if you notice, I don't have a number. I'm going to put here, depending on what Dr. Daly has in stock, we either have 1 or 2 octane. And then you have limonene and naphthalene. If you're not sure of the structure, guess what? You can look them up on the internet or come to my office hour and I'll help you out. Now, the second part deals with a very classic reaction that helps identify double bonds in a molecule. And before organic chemists had the sophisticated electronic equipment like infrared spectrometry, also nuclear magnetic resonance, which is NMR. Organic chemists had that before they started using that in hospitals for imaging. And they took from what organic chemists knew and added some things to it. And that's how that became useful, very useful in hospitals. Now, let's look at the following. All right, everybody see my whiteboard? I haven't been checking, but if you can't see something I think you should be, let me know. As your colleague who let me know, thank you from before. All right, you have a double bond and you react it with a halogen. You break the bond and each carbon gets a halogen. Now, for this reaction, for this lab, and I would do this as a demo because I used to let students do this, but they don't know how to handle properly bromine in solution. And at the other school, I actually had a student, it was an accident, get bromine solution on the back of the neck of another student. And after that, I said, this is too dangerous, and bromine on your skin is very hazardous. It burns real quick. It reacts with your skin real quick. Then I said, I'll do this. Now, same thing happens, but this is clear. Most organic chemicals, not all, or a slight yellow. This is clear or slight yellow. This is, depending on the concentration of the solution that's made, is a reddish brown color. And if there were no double bond and you added something reddish brown to that solution that's clear, that chemical, it would turn reddish brown. So when you add bromine to a compound, and if it does not change color, that tells you the compound has a double bond. And that's what you would be watching me illustrate. I thought I could delay this. Hang on, I gotta close these. Sorry about the delay here. Oh, what am I doing this? I'm doing it the hard way. All right, we're back in action. All right, sorry about that. And now let's take a real quick look at YouTube. I think everything's in YouTube but my college graduation, my PhD graduation. But all right, thumbs up, people. Do you see alkene on your screen now? That's the bromine solution, alkane. See how it's getting colored a reddish brown? And you see me do this for a number of them. And now for the alkane, see how quickly that bromine is reacting with the double bonds in that test tube? You put that in there and it's not changing color. And that's how you can distinguish an alkane from an alkene if you don't know and you don't have modern equipment. We have modern electronic equipment that now will allow us, but for this lab, I want to teach you some of the old ways that are still very active. So in this lab,
So I've got my essay written and I've been working on it for about a week. So now I'm going to show you how I use Grammarly.
hold on.
Okay, so here's my essay and I'm going to click through Grammarly suggestions in the right.
It happens when I forget to turn that off. All right, everybody see the lab on their screen now? Nope. Now do you see wear rubber gloves on your screen? Okay. All right, now I'll do this. What I do is in a test tube, put about 5-10 drops or whatever I'm going to test, then add some bromine like you saw in the video, wait about 2 minutes and then dispose of it. Now, if we were in a lab, you'd see me take cyclohexane, and it's red-brown. One cyclohexene would be clear. And let's make this, because we did it earlier, 2-octane clear, limonene clear. And to make this exciting, the district attorney of Kane County contacted us. I have the sample and I have to know, does it have a double bond or not? Actually, I have 2 samples and I have them cleverly named unknown A and unknown B. And when you add bromine to unknown A, it becomes stays clear. When you add it to unknown B, it goes red-brown. And you'll see later on the questions, this is important data you need to know. All right, the last one, part 3, is called identification of alkenes via oxidation. Now here, if I have a double bond, this is one way of drawing any double bond, and react it with potassium permanganate, KMnO4. And this is a reaction I didn't teach in the lecture. And let me remind you, anything we do in the lab will never be on a test in the lecture, and I don't give lab quizzes either. Now, what happens is you break the double bond, and each carbon gets a hydroxyl group. Now, this is called an oxidizing agent. When it oxidizes the double bond, it gets reduced and forms manganese dioxide, which is a brown color, also muddy brown. Sometimes you also get other manganese compounds, which are green. So if you start out with something clear and you add potassium permanganate solution, which is purple, and you get muddy brown, which I call this muddy brown, that tells you you've got a double bond in the solution. So what are we going to be doing? In a small test tube, and this one you do yourself, you'd add about 10 drops of the potassium permanganate solution. This is already made up for you. We'd have them in hoods, and I have different samples, and each of the alkanes or alkenes you're testing, you'll put about 5 drops. If you mix it, and ooh, that reminds me. Here we go. Even though you're not going to be doing this, if this were a test tube in a lab, you never ever shake a test tube like this, because you can get chemical on yourself or other people, including the instructor. Not good. One way to mix chemicals in a test tube, they're only about this big, is you hold it firmly and you hit it this hard with 2 fingers about 3 or 4 times, and it mixes it. You don't tickle it, because that won't mix it. You really got to hit it hard. Now, we also have in our labs, we got a number of years ago, they're called Vibro Mixers. There's a motor, a round disc, and you can adjust it. And I do hold the test tube, push it down, and this vibrates like that, and it mixes it, and they're fun to play with. And students like using that. And let's look at the following video. Sorry about the ad.
Naphthalene addition of bromine to alkenes provides a convenient test for the presence of a double bond in the molecule. Shaking a liquid alkene with brown-yellow bromine water results in the decolorizing of the solution,
This you've
giving
already
the formation
seen.
of a colorless dibromo compound. Gaseous alkenes, such as ethene, can be detected by passing them through bromine water with a similar result.
Coming up is the potassium
An
permanganate.
alkaline solution of potassium manganate 7 oxidizes alkenes to the corresponding diols.
See how purple potassium permanganate?
Dark purple manganate 7 ions are reduced to insoluble brown manganese 4 oxide, which produces a turbid brownish suspension.
I don't know why I couldn't get rid of that pop-up. But anyways,
Dark purple manganate 7 ions are reduced to insoluble brown manganese 4 oxide, which produces
nope, it won't let me get rid of that. But anyways, you can go back and look at the video on your own. And for this lab, if we had been in the face-to-face, you would do this yourself. You do hexcyclohexane, that stays purple. You put in one hexene, muddy brown, there's a double bond there. And let's do this 2-octane, muddy brown, limonene, muddy brown. And then we got those two unknowns, unknown A and B from the Kane County District Attorney. And when you can help identify, does they have a double bond or not, that district attorney can now convict something of a very heinous crime. I'll let you fill in the blank what the heinous crime is. And that's unknown A. When you do it, it's muddy brown. And when unknown B, you put the potassium permanganate, it's purple, stays purple. And that's the lab. Now, please use your experimental results to justify your answer. First of all, I'm asking you to draw the structures again. And here, number 2, what's the reason? The color of dilute KMNO4, potassium becomes muddy brown when adding an alkene. Explain with a chemical equation and words how the solution of bromine, added to the alkene does not cause a color change. And then number 4, identify unknown A and B as not the actual chemical. All I'm asking for is A an alkane or an alkene? Is B an alkane or an alkene? And use parts 2 and 3 to describe how you know this. And that's today's lab. And that's today's class. We got out about 5 minutes early. Starting next week, I'm just about caught up for the late start we had, and we'll be getting out a little earlier for Wednesday lab. And remember, the lab we did last week is due today or tomorrow. Get it in on time, it helps me. And this lab is due next week. And I have my office hour tonight. And don't forget, if you'd like a little later start, email me and let me know. And if enough people do, I'll change it. With that, I'll say Gang Gesund, which is going health in Yiddish, Gang Gesund. Have a nice rest of the week and weekend. And if I don't see you at my office hour, I'll see you next Monday. Gang Gesund. Don't forget to think about gas station alkanes and do the practice problems, because next week is test number 1. And on Monday, I will go through the aromatic problem set and I will do my world famous review for the next test, test number 1. With that, I'll say once again, Gang Gesund. Bye now. And I stole that from Granny and the Beverly Hillbillies. Bye.